This one over here would finally be xm minus 1 at the other end of the constellation. And so therefore the message indicator m itself is 0, 1, up to m minus 1. And it turns out that we can actually immediately translate the message indicator, which is going to be some bits. If we get a few bits coming in, we're going to change that into some kind of number, some positive number between 0 and m minus 1. And we can actually write out that the symbol value is 2 times the message minus capital M plus 1, if you will, times d over 2. And that will always give you the value along the line. Okay, so you could do that in digital signal processing if you wanted. Take the message, okay, it's a few bits. If it happened to be 4 bits, it's some number between 0 and 15. So you take 2 times that number, subtract off 15, add 1. Sorry, subtract off 16, add 1, which is the same as subtracting 15, and multiply by whatever distance you want over 2, and that will give you the right point along the line. Okay, so that doesn't look too bad in terms of implementation, which is why PAM is very popular. Take the message M, and then you would run through some kind of simple adding device, really, where we would have another way of writing this is take the message M minus m minus 1 over 2, which is some constant, times d. Out comes x. Probably run this through now a digital to analog converter. Now we've got messages between 0 and capital M converted into actual real numbers that are both positive and negative. Run that through a digital to analog converter, and you can think of that perfect analog to digital converter as essentially taking x, which is a number, and multiplying it by a delta function in time, and running through then our basis function phi of t, which, as we said earlier, is usually some kind of low-pass filter, and out comes x of t, our modulated signal, ready for transport over the data transmission channel. And typically, if this is low pass here, then this will be a low pass channel. That's the way it's been designed. Now note, independent of this filter, okay, the probability of error is going to be a function of the constellation. It's going to be the number of nearest neighbors, whatever that happens to be. For binary, it was just one nearest neighbor. We'll have to figure it out for the other ones. We'll do that momentarily. Times q of d over 2 sigma. So we already know the probability of error, okay, independent of what this actual basis function details would be. Now, what kind of basis function might be typical? Well, typical one would be phi of t is equal, to normalize it, I have this factor out front, 1 over square root of t, times the sinc function, t over capital T. Now, some of you may recognize that sinc function, I'll tell you what it is in a second, as corresponding to an ideal low-pass filter. In fact, its Fourier transform is going to be something that goes from plus 1 over 2t to minus 1 over 2t. It's going to be normalized by this factor, so the area under the square of this is going to be 1. And what you can see from this, if you inverse transform, is that this function here is sine of pi t over pi t over t. So sinc of x is sine pi x over pi x. All right, and it's got this nice kind of character to it that, and I suspect many of you have seen the sinc function before, where essentially it is 0 at all sampling instants except 1 times 0. So if I look here at minus t plus t, it goes through 0, t minus 2t. And clearly, if I were to send messages separated by capital T units in time, what's going to happen is if I have one coming a little bit later, if I have one that's sent at time 0 and another one that's sent later at time positive t, then its sinc function is going to look like this. And clearly, if I sample in a receiver, which is going to be easy, if this is the basis function, it's another ideal low-pass filter, okay, and I sample at all multiples of the symbol period, all of the other sinc functions are 0 then. So I'm completely independent of all the other messages that were transmitted. So this was a nice basis function to use if I want to send PAM signals one after another, and not have to worry about them interfering with one another in transmission. Up to this point in the class, we haven't really thought about sending more than one message. Okay, and suppose they overlap is, of course, the question. What do you do to resolve them? We're going to have a whole section of the course on that. It's called equalization in Chapter 3, which we'll get to later. But for now, if we actually had an additive white Gaussian noise channel, then clearly it is not adding any additional filtering to the channel. The match filter and the basis function are essentially the same thing. If I stick in minus t here, I just reverse it in time. And then if I offset it in time, all I'm doing is changing the point that I send the message through the channel. Okay, so that is kind of a nice system for transmission. If I were going to go ahead and make decisions, I would have y of t. TV, if you could have the overhead. There we go. Then I would run through the ideal low-pass filter we just talked about. I would sample at all multiples of the symbol period now. And then I would run through an analog to digital converter. And out would pop X at this point, the symbol value. And then I would go ahead and make a decision on that. I could do that by essentially adding minus d over 2, a neat trick to this, and then truncating, just lopping off bits. And you would find, in fact, that that picks the closest point. If you look at that particular, you can do it any way you want, but that might be a nice implementation that will pick the closest point. Okay, and we know that for the additive white Gaussian noise channel, that's what the optimum receiver does, is it looks at whatever the received value is. I should really put x hat here because I've got some noise. Or equivalently, this is y is equal to x plus n at that point, and then I'm going to pick the closest point. So this is a pretty easy system to deal with if there's no filtering in the channel. I've got an easy transmitter, easy receiver, kind of a nice system. Now, the exact expression for probability of error, we're almost there already. We know that the minimum distance is the same between all the adjacent points. It's d. We constructed the PAM constellation that way. The number of nearest neighbors is pretty easy, because if I look at my constellation, let me just show it to you again here. Every one of these points has two nearest neighbors except for the ones on the end, and they only have one nearest neighbor. Right? So that's not too hard. So what I have then is 2 out of a total of m messages have only one nearest neighbor, and the other m minus 2 of those m messages have 2 nearest neighbors. And so that tells me, with some algebra, this is 2 times 1 minus 1 over m. My probability of error is then 2 times 1 minus 1 over m, q. And it's actually not an upper bound in this case. If you look at it, you can see that you don't need to put the less than signal for PAM. It's actually an exact expression of d over 2 sigma. So if I know the distance, then I know sigma. Now let's just look at a few cases of what d is equal to if we pick different size constellations. Let's suppose m is equal to 2. All right. Well, then the probability of error is equal to 2 times 1 minus a half is a half. Well, that's 1 times q of d over 2 sigma. Now, if I look at only 2 points in the constellation, clearly the energy per dimension is d squared over 2, because they're both the same size. So what I have here is d over 2 over sigma. This is square root of what we called the signal-to-noise ratio earlier. So that's the probability of error for binary transmission with PAM. Notice I have this signal-to-noise ratio inside the Q function right now rather than writing d over 2 sigma. That may be an easier thing. We kind of know the ratio. I don't even have to know what d is. I just need to know what the ratio of the signal power is at the output of the channel to the noise power, and I've got the probability of error. Yes, sir. Remember to use the mic.
It seems like every constellation we've studied so far, when you go down to 2 points, this seems to be the equation.
Yeah, and that's going to be, any good system will have that property.
Okay.
And unless you get into coded systems, and we'll actually be able to get a coefficient out in front of the signal-to-noise ratio that's greater than 1 and improve it. But you won't see that in 379A. 379B we can actually do better. But the simple types of constellations, QAM is going to have the same formula, it turns out, as this. And that's about as good as you can do with simple transmission methods. The case for m equal to 4, it gets a little more involved. Now I'm going to have a probability of error that's 2 times 1 minus a quarter. 2 times 3/4 is 3/2. And now I'm going to get Q of d over 2 sigma. Okay, well, fine, I can leave it as Q of d over 2 sigma. Let's play with it a little bit and see if we can't figure out what Ex bar is in terms of d or d squared. Well, Ex bar, there are 4 points in the constellation. Obviously, the positive ones have the same magnitude as the negative ones. So what I have is 2 points, so occurring half the time, which have magnitude of 1 squared, plus another 2 points that have a magnitude of 3 squared, and of course, all of these things were multiplied by d over 2 squared. So this is my average energy. So I've got here 1 plus 9, which is 10 over 2, which is 5. So this is 5 times d over 2 squared. So I look at that, okay, come back up here to my formula. It's going to be square root of SNR over 5 for 4 points. You can see the SNR occurring. SNR is fundamental. It's not really the d or the sigma. It's the ratio of the two that determines the probability of error. In this case, to send 2 more messages, because with respect to binary, I only had 2 messages here. Now I have 4. So to send the extra 2 messages, I need 5 times as much signal-to-noise ratio. Channel's got to be better. Higher signal-to-noise ratio, better channel. Now 5 happens to be 7 dB. If I take 10 log of 5, I get 7, or 7 dB. So this tells me that my signal-to-noise ratio needs to be 7 dB higher to send an extra bit going from 1 to 2. Now remember we talked about earlier that some people can't understand how do you get, 10 megabits per second through a channel that only has 1 megahertz of bandwidth. Well, you can see what's starting to happen here is if we happen to have 1 megahertz of bandwidth here, but we were sending 2 bits per symbol, we'd have 2 megabits per second being transmitted. And we need more signal-to-noise ratio. Higher quality channels with higher signal-to-noise ratio can have a lot more bits per second than the actual bandwidth of the channel itself. You remember from the basis function that our symbol period, I had it drawn over here, the symbol period was 1 microsecond, or equivalently 1 over t was a megahertz, then this system basically has a bandwidth of 500 kilohertz, or if you count negative frequencies, it has a bandwidth of 1 megahertz. So it's possible to do that. Now I could continue. If I have higher signal-to-noise ratio with PAM to transmit more and more signals. And I have a derivation of this in the notes. You got to get into some algebra. But basically, you can relate for a general M that Ex bar, the energy per dimension, works out to be d squared over 12 times m squared minus 1. You can see that works in this case when m was equal to 4. We've got 16 minus 1 is 15. 15 twelfths is the same as this 5 fourths that we have here in that case. So this works in general. And so therefore I have a probability of error for PAM, which is 2 times 1 minus 1 over m, the number of nearest neighbors, times q, and then reversing this back to the form that we can use the signal-to-noise ratio, what you'll get is 3 over m squared minus 1 times the signal-to-noise ratio. Now you can see when m is equal to 2, I get 3 over 3, so that factor goes away. When m is equal to 4, I get 3 over 15, which is 1/5, which is what we just showed. And in general, we can plug this in. I need more signal-to-noise ratio to send more bits per second through the channel. And that's true of PAM. It's generally true of a lot of other types of modulation types also. So that's how you do it. What's the largest number of bits per dimension I've seen, or bits per symbol used in PAM constellations? I've seen basically up to, you can see systems that will actually transmit as many as 7 or 8 bits per dimension, which means that m would be a number like 256. Is about as high as, and that's going to occur on systems that have very high signal-to-noise ratios to be able to do that. If I got 256 here squared minus 1, that's like 16,000 in the denominator here, so we need an extra 30, 40, 50 dB, in other words, a factor of 10,000 or more signal-to-noise ratio than we might need for binary transmission in order to do that. That's a really clean channel that has a high signal-to-noise ratio like that. But that can happen in transmission. Let me put this in tabular form. Now that I've got you thinking of how many dBs or how much signal-to-noise ratio does it take to send data, there's a table in the notes. I'm just repeating it here, so don't try to copy all this down. I'm just going to go through the number of bits I would send. Then in the next column here, next column I will convert that to the number of levels. So here's 1632. And I'm going to look at d over 2 sigma, that's the argument of the Q function, for the Q function to be equal to 10 to the minus 6th. Okay, so you could go back in Appendix A of Chapter 1, and you could look at the curves there, and you can read off and say, where is it, 10 to the minus 6? If you did that correctly, you'll see that this occurs when d over 2 sigma is 13.5 dB. So that means that 20 log of d over 2 sigma, which is equal to 10 log of d over 2 sigma squared. Decibels are always the same. There's not a 20 dB form of decibels and a 20 log form and a 10 log form. They are both the same, always. Okay, so don't let yourself get confused on decibels. It's 10 log of a power ratio or equivalently 20 log of a voltage ratio in doing that. And d over 2 sigma, this is always going to be the same because that's the argument of the Q function if I want to get 10 to the minus 6th as a probability of error. If I want 10 to the minus 7th, it turns out it's 14.2 dB. Okay, but that d over 2 sigma, we need that argument to be equal to this number. For a signal-to-noise ratio to lead to this argument being 13.5 dB, for 1-bit transmission, 2-level transmission, we already saw that that was also the argument of the Q function, 13.5. But for 4-level transmission, 2-bit transmission, we saw we had to have a factor of 5 or 7 dB more, so this needs to be 20.5 dB. So that means 20 dB means that the power of the signal is 100 times bigger than the power of the noise. So that's starting to look like a pretty clean channel. If I want to send 3 bits, it turns out by working backwards from the formula, I need 26.8 dB. So yet again, almost 7 dB of increase. Now what happens, actually 6.3 at this point, and if we continue, you'll see these numbers show up. And what I would like to do is just call it signal-to-noise ratio increase. To go from there to there, I needed 7 dB. Here I needed 6.3. And you'll see, if we were to continue this table ad infinitum, this number would always be 6 dB. It's basically 2 squared or a factor of 4, and that falls out of the denominator here. The one term becomes so insignificant with respect to m squared that basically every time I double m, I get a factor of 4 here. That's the 6 dB increase. So you see this rule in PAM systems often quoted, not quite exact down at low levels, but I need